What's up, everyone? Welcome to Ask a Chemist. Today, we're going to be talking about substitution reactions of haloalkanes. So when you think of organic compounds, think of them as being in families of compounds that can be placed into groups. All of the families within a group react in similar ways. There are different major groups of compounds, and the haloalkanes are one of the groups that we'll find in these families. So once again, what is a haloalkane? A haloalkane is a compound that consists of a halogen and an alkane. Where can you find the halogens? These are in group 7 of the periodic table. The main halogens that will take place in substitution reactions are chlorine, bromine, and iodine. If you look below, there are some examples of haloalkanes that contain these common halogens. An alkane, once again, is just a hydrocarbon. It's made up of carbon and hydrogen atoms. So we've got methyl chloride as an example, methyl bromide, and methyl iodide. These are all haloalkanes. Now, if you notice, all of the example compounds that I have here can be found in the same group as the haloalkanes. They all have an electronegative atom that is attached to an sp3 hybridized carbon atom. This electronegative atom or group creates polarity in the bond between it and the sp3 hybridized carbon atom. And this is what makes it possible for the compound to undergo substitution and/or elimination reactions. So let's look at these examples that we have here. If we look at our first example, we've got methyl iodide. This is a haloalkane. The polar bond that's found in methyl iodide is between the carbon and the iodine. I'm going to circle all of these polar bonds. Our second compound is methanol, and we have a bond between carbon and oxygen. That is our polar bond. In our epoxide, we've got two sp3 hybridized carbon atoms that are both bonded to an oxygen. These are our polar bonds. I'm only going to circle one of them. In the last compound, we have an ether that's got two sp3 hybridized carbon atoms that are both bonded to an electronegative oxygen. And I'll just circle one of these bonds, and that's our polar bond. So let's begin by discussing the patterns that are observed in substitution reactions. The main pattern that we see is that a bond breaks at an sp3 hybridized carbon atom and another bond forms at that same carbon atom. Or to put it differently, atom that is bonded to this sp3 hybridized carbon atom changes. So here our bromine changes to a cyanide. Everything else stays the same. So let's go ahead and number these carbon atoms so that we can more clearly see what's going on. Let's designate carbon 1 as the carbon that is bonded to the bromine. And let's also number the carbons in our product. Carbon 1 is going to be the carbon that is bonded to the cyano group. And then we're going to go back and we're going to circle our polar bond. So in our haloalkane, the polar bond is between the carbon and the bromine. And in our product, the polar bond is between the carbon and the cyano group. So now the next part is really easy for us to do. Which bond is broken and which bond is formed? Well, we've already circled it. The bond that breaks is the bond between carbon 1 and bromine, and the bond that forms is the bond between carbon 1 and the cyano group. Let's do another example. So in our second example, we are also starting off with a haloalkane, an alkyl bromide, and let's just first of all designate which carbon is the one that we believe to be where the reaction is going to occur. And that's this carbon here. So this is an sp3 hybridized carbon. It's bonded to bromine. So this is going to be our polar bond. And in our product, our polar bond is the carbon that is bonded to the hydroxyl group. Let's go ahead and let's number our carbon atoms. So if we look at the parent chain, it's going to be the longest chain in the compound. we start from here, number that as number 1, and this makes up our parent chain. Let's also number the carbon atoms in the product the same way. And we've already answered the question of which bond is broken, which bond is formed. The bond that breaks is the bond between carbon 2 and bromine. And the bond that forms is the bond between carbon 2 and the hydroxyl group. We're not going to pay attention to the side products really because those are ionic compounds. They're inorganic. We're only concerned about organic compounds in organic chemistry for the most part. Let's do one more example. Now this example is different from the first two because we're starting off with an alcohol instead of a haloalkane. So this alcohol has a polar bond. The polar bond is going to be between the carbon and the oxygen, and we're going to circle it. And in our product, our polar bond is between the carbon and the chlorine. So let's go ahead once again and let's number our carbon atoms. It doesn't matter which side we start from because this is a symmetric compound. So there's a line of symmetry going down the central carbon. And then we'll also number the carbon atoms in our product in the same fashion. And then we see that the bond that breaks is the bond between carbon 3 and the hydroxyl group. And the bond that forms is between carbon 3 and the chloro group. So this is really straightforward. Now, let's go a little further in preparation for the next video. And we'll see that when organic chemists perform experiments that involve these substitution reactions in the lab, they notice several things. The first observation is that when chemists measure the reaction rate, they notice that the reaction rate depends either on the concentration of 2 different species, or the reaction rate only depends on the concentration of 1 species. So looking at the top reaction, we have an alcohol. This alcohol is treated with hydrogen bromide to form a haloalkane. The reaction rate depends here on the concentration of the alcohol and on the concentration of hydrogen bromide. So it depends on 2 things. However, on the bottom, the same thing is happening in the sense that we have an alcohol being treated with hydrogen bromide and it's going to form a haloalkane. However, on the bottom reaction, the rate only depends on the concentration of the alcohol. Think about why this might be the case. I'll give you a little hint. Look at the type of alcohol you're starting off with in both reactions. Now, our second observation that chemists make is that in some cases, the reaction rate depends on the type of haloalkane. So in this instance, primary haloalkanes react slow, but tertiary haloalkanes react fast. So at the top here, we have what we would call an alkyl bromide. And this is a primary alkyl bromide because there's only 1 carbon that is bonded to the bromine. And it forms a primary alcohol. This primary alkyl halide gives us a slow reaction. On the bottom example, we have what we call a tertiary alkyl halide. And this is tertiary because there are 3 carbon atoms that are bonded to the carbon that is bonded to the bromine. So this carbon here is bonded to the bromine. There's 3 other carbons that are directly bonded to it. That's what makes it tertiary. It forms a tertiary alcohol. And this reaction occurs very fast. So once again, why do you think that this is the case? In our third observation, sometimes the reaction rate depends on the type of haloalkane, like in the second observation, but it's the primary haloalkane that reacts fast, while the tertiary haloalkane doesn't even yield a substitution product. So this is crazy, right? You've got 2 haloalkanes They undergo a reaction, and one of them doesn't even give you a substitution product. So it's not even a substitution, it's an elimination. So let's look at this slowly. At the top, we have a primary haloalkane. This is primary once again because the main carbon that is bonded to the bromine is directly bonded to only one carbon. So that makes it primary. This is being treated with a base called sodium hydroxide, and we form a primary alcohol. It tells us that this gives a fast reaction. However, on the bottom, we have a tertiary haloalkane. It is also being treated with sodium hydroxide, but we get an elimination product. So water is eliminated and sodium bromide forms as well. Now, why in the world would this happen? Are you confused yet? Well, hold that thought because there's one more observation. In our fourth observation, some molecules have the ability to rotate plain polarized light. So in some substitution reactions, molecules that have this ability, which is known as having optical activity, they keep their optical activity. But in others, this optical activity actually goes away. So if we look at the top, we have a compound that is going to keep its optical activity. In the bottom reaction, there's no optical activity that is retained. So how in the world do we explain these observations? What kind of hypotheses can we come up with to clarify all of this? This is what we're going to talk about next time. Today, we had an introductory discussion about the substitution reactions of haloalkanes, and I provided you guys with some examples of them. Next time, we will be talking about SN2 reactions. So thank you guys for watching. Remember to subscribe and follow me on social media and send your questions and commentary to Amakemist. See you guys next time.